All right, welcome everybody to our weekly seminar, the MCube Weekly Seminar. Today we're very happy to have George Kiladis from NOAA. George is a research meteorologist. Where is George? You come back in? Oh, you got again. All right, he's a research meteorologist at NOAA's Physical Sciences Laboratory here in Boulder. He received his PhD from the University of Colorado in atmospheric sciences in 1985. And he worked at Ceres for 10 years before joining NOAA in 1995. George's main research interests include equatorial waves, tropical, extratropical interactions, the coupling between tropical convection and the large-scale atmospheric circulation, and statistical analysis that can be used to improve numerical models. George is a fellow of the American Meteorological Society. In 2018, he gave the AMS Bernard Horowitz a memorial lecture, and in 22 he received the AMS Jewel Charney Award. So today we're very fortunate to have George here to tell us about the dependence of the structure of stratospheric Kelvin and mixed Rossby-gravity waves on the background flow. George?
Thanks, Rich. Oh, this. Yeah, it's been quite a while since I gave a talk in this room, but it's great to be back and see everybody in person. Okay, how's that? Can you hear me? Or should I move that up? Oh, thank you. How's that? Okay, great. Okay, so yeah, I'll be talking about Kelvin and mixed Rossby-gravity waves in the stratosphere. And this is work with John Albers and Juliana Diaz from Physical Sciences Lab, and also Hamid Pahlavan, who provided data and expertise. And Hamid now sits across the street at Northwest Research Associates, working with Joan Alexander. So the questions I'll be addressing today are what the dominant scales and structures of Kelvin and mixed Rossby-gravity waves are in the stratosphere, and how these scales and structures vary with the QBO. The other question that's very important is to what extent we can use reanalysis products to answer these questions here. And with regard to that last question, Hamid recently led a study where we looked at the momentum forcing of the QBO using ERA5 reanalysis data, and that's the data set that I'll be using in this talk here. And this seemed to work out pretty well. I would say this might be probably the best, most recent estimate of momentum forcing of the QBO. So in the shading here, you can see the EP flux divergence, which tends to be concentrated in these shear zones. So, and a lot of work in the past have concentrated on this process of what drives the QBO. But in this talk, I'm going to be focusing instead on these extreme times of the QBO, the strongest easterly and strongest westerly times, as you see descending over time in this time height diagram here. So yeah, contours are the zonal wind. And so yeah, what we're really interested in is how the background flow affects the state of these Kelvin and mixed Rossby-gravity waves rather than the momentum forcing of the QBO itself. So I'm going to start off showing a bunch of space-time spectra of equatorial, zonal, and meridional wind at various levels in the stratosphere. And then we're going to, that'll be for mean conditions, and then we're going to look at those spectra for QBO extremes. And then we're going to look at EOF analysis of Kelvin and MRG wave structures for QBO extremes and see how those vary with respect to that background state. And we're going to examine potential impact of damping using a simple parameterization under various background flow regimes. And yeah, I'd like to emphasize that much of what we're going to be looking at has been looked at before in satellite data, but reanalysis, if we can trust it, provides a really convenient data set to look at the vertical and horizontal structure and the wave activity changes over time. And the other point I'd like to emphasize is that the techniques I'll be outlining here are very straightforward and suitable for both reanalysis into comparison or model verification. And one example, we recently, with Young-Ha Kim, looked at various reanalyses using the EOF approach that I'm going to be talking about here. And it turns out that the various reanalyses that we looked at were pretty similar in terms of Kelvin wave structures and variability, but not so much for mixed Rossby-gravity waves. So that's still a question we have to grapple with. Okay, so detecting these stratospheric waves is very easy. This is Hofmuller diagram, Greenwich to Greenwich, so it's global zonal wind along the equator only. And the only thing I've done here is taken out the zonal mean, so no filtering involved at all. Time's going up here. So you see these prominent eastward propagating disturbances, which are Kelvin waves for the most part. Typical phase speed up here is 34 meters per second. And it turns out that this period coincides with a descending westerly shear zone in the stratosphere, in the QBO. And what you see here is actually quite typical. During QBO easterlies, Kelvin activity is more confined to the Indian Ocean, Eastern Hemisphere, and then it becomes more organized and more dominated, in fact, by wave number 1 and 2 structures when you have QBO westerlies. Whereas in QBO easterlies, the structures tend to be more confined and composed of higher wave number components as well. And this is actually quite systematic, it turns out. Okay, at the same time, what's going on in the meridional wind is shown here. So we start out in this QBO easterly phase where we have these interesting standing oscillations in the meridional wind along the equator. And then as we progress to QBO westerlies, we start seeing westward propagation here. So these are mostly the signal is mostly due to mixed Rossby-gravity waves. And even though we have a westerly background flow developing in this descending QBO westerly phase here, these waves are swimming upstream against that westerly flow. This is just another example. This is very common with this standing QBO easterly situation here, and then progressing to propagating features as we develop westerlies. And I'll show you that statistically that's what you see over the long term. Okay, just a reminder, the structure of Kelvin waves is shown here from Matsuno. Kelvin waves have in-phase geopotential in the shading and zonal wind perturbations, which peak on the equator, and they have a symmetric structure about the equator. And mixed Rossby-gravity waves are these gyres centered on the equator with an anti-symmetric structure in both the zonal wind and the geopotential. So to look for signals in space-time spectra, we can look at symmetric, the symmetric zonal wind, in this case from 15 south to 15 north. And this is a space-time spectrum of the zonal wind in this latitude band for the entire data set, 1979 to 2018 in ERA 5, the 50 hectopascal zonal wind in this latitude range here. So these diagrams go from 96-day periods to 1.25 day periods, and then westward waves 1 through 10 on the left, eastward waves on the right. So you can see the general red structure in the power in space and time, but very prominent spectral peaks also show up. And if we remove a background, just divide through by a smooth background from the raw spectra, we bring out these spectral peaks you see here. And these correspond to, up here, westward inertial gravity waves, Kelvin waves, and these external Rossby modes with the 5-day wave showing up here, for instance. Chris?
Could you take me back through 2 points here? One is what's happening with the meridional structure. What are you assuming or not assuming about
Yeah, so
FFT along the equator? Or it's
yeah, so in the case of the Kelvin wave, it has a meridional extent, so that's why we average. When we do those spectral analyses, we do them at each latitude and then just average after doing each latitude. Yeah, we're not averaging first and then doing.
okay, and then when you took out the backgrounds,
Yeah.
say what that meant?
Okay. You know, just like if you were to do a frequency spectrum, you would estimate a red noise background, say, using lag-1 autocorrelation. We don't have an objective, completely objective way to do that in space and time. So we just do a very ad hoc thing. We take the raw spectra, symmetric and anti-symmetric, and we just smooth the heck out of it in space and time and end up with a relatively smooth background. In principle, you might think that that should be symmetric eastward and westward. In other words, you know, just something that would just look like this. But, you know, there's background wind influences and so on. I mean, we don't care so much about the quantitative aspects of this process. What we really just want to do is bring out these spectral peaks so that we can figure out how to, for instance, filter for these particular modes.
Okay.
Does that make sense? Okay, yeah. So, yeah. So yeah, so you know we know this is where most of the power for the Kelvin wave lies in space-time from doing that process. Okay, so yeah, and we've superimposed these dispersion curves for the Kelvin wave you see here, and the peak at wave 1 down here. So that's another thing. You can see that these peaks are discretized at wave numbers, and that actually makes physical sense when you realize that in the stratosphere, Kelvin waves do tend to be planetary scale and discretized in waves 1, 2, and 3 primarily, at least in the lower stratosphere. So the spectral peak for wave 1 features lies at about 120 meters with an implied phase speed of about 34 meters per second, which matches that phase speed that I showed you in that earlier Hofmüller diagram. Okay, and you can see there's a broadband in that signal. It's broadband in frequency and in wave number, which means there is some variability about that scale. Okay, so now that was 50 hectopascals, so lower stratosphere. Now we drop down to 100 and do the same thing for the zonal wind again in this latitude band. And we can see there's a Kelvin peak here, westward inertial gravity wave peak here. But if we toggle back and forth between 50 and 100, it's obvious that this spectral peak matches more like a 50-meter equivalent depth. In other words, these waves at 100 at the tropause level are moving quite a bit more slowly than the waves further up in the stratosphere. Same thing for the westward inertial gravity waves. And as we go through these, you might notice that these external Rossby modes don't change scale at all with height. So what I'm going to do now is go up from 100 into the lower and then upper stratosphere. Right. So another point I want to make is that this is the same exact procedure for outgoing long-wave radiation. And in this case, we see a pretty good match between the scale of the OLR peaks here, at least in this Kelvin band, and the zonal wind at 100 hectopascals. And then there are other features like the Madden-Julian oscillation that show up here. I won't show you, but I can tell you that the coherence between the zonal wind at 100 and the OLR signal that you see here, the coherence in time is very high. So in other words, this spectral peak in the zonal wind at 100 is pretty much a forced response from convectively coupled waves in the troposphere. In other words, if you have a convectively coupled Kelvin wave, it forces a zonal wind response at the tropopause level that is sort of dragged along with the convection. Now, what we're going to do is back to 100. We're going to go up to 70. Now back to 50, which I showed earlier, and up to 30. Okay, so what you see as you go up further into the lower stratosphere is an increase, two things happening really. A decrease in the power at lower wave numbers and an increase in the equivalent depth. In other words, the speed, now we're at 10, of these Kelvin waves is larger and faster as you go up into the stratosphere. And this has, of course, been known for quite some time from satellite data. As you go up now towards the uppermost stratosphere in the region of a semi-annual oscillation, these are the so-called ultra-fast Kelvin waves that are moving more like 60 or so meters per second. And these waves can be pretty much considered free modes that are launched at the tropopause level, most of which are excited by convection. We'll be talking about that a little more in a couple of minutes. Okay, the same thing for the antisymmetric zonal wind is shown here, and this picks up mixed Rossby-gravity wave signals quite well. And I'll just quickly run through this just to show that the same thing happens in this mixed Rossby eastward inertial gravity wave continuum. These waves move faster and faster as you go up in height in the stratosphere. And by the way, I just want to mention one thing. People focus on these westward propagating mixed Rossby gravity waves, but in fact, this is a continuum, and you can't actually ignore the eastward side. That's a story for another day. But they are more or less active at the same time. So it's a continuum. And the reason the westward propagating features dominate is because the Ross spectrum, as you saw earlier, at least for zonal wind, is red. And it's likewise for this antisymmetric component, red. So the lower frequencies, you can see just due to the shape of this curve here, the lower frequencies over here will dominate. So westward propagating features dominate in this antisymmetric zonal wind. Okay, again, this sort of thing has been known for a long time, and Rolando Garcia and Murray Sauby wrote a couple of classic papers which beautifully describe how this works, and it's basically due to damping. So we parameterize damping by this simple method where this scale-dependent damping coefficient comes out of Fels, 1982. That's primarily due to radiative cooling. And you can see the damping is proportional to wave number, but also proportional to the inverse of frequency squared. So that's what's dominant in terms of the damping as these waves propagate vertically. And basically, this is inversely proportional to the vertical group velocity. So in other words, lower frequency waves, which have a slower upward group velocity, have more time to get damped. So this damping basically filters out the lower frequency components more strongly with height, which is why you see higher and higher frequency waves as you go up. Okay, so far I have ignored the background state. I've used the entire data set, which includes a bunch of QBO easterly and westerly background states. But now what we're going to do is we're going to condition spectra on two samples, QBO westerlies and QBO easterlies. And this is just based on a plus minus 1 standard deviation of the zonal mean, zonal wind along the equator. And we do this by month. So we take months of QBO easterlies, which we have 117 months of, and then another sample where we have 109 months of greater than 1 standard deviation of the zonal wind. And here's what the basic state looks like for the QBO easterly sample. The easterlies peaking at about almost 15 meters per second along the equator with this broad meridional extending out to 20 north and 20 south. This is, of course, including all seasons. If you do this seasonally, there is some latitudinal shifts, but for the moment, we're going to ignore that. And we're just going to look at all QBO easterly, QBO westerly months. This is the QBO westerly sample, zonal wind, again peaking close to 15 meters per second along the equator. And you can see that it's much more equatorially trapped compared to QBO easterlies, which extend out to 20 north and 20 south. So there's a lot of meridional shear, especially in QBO westerly state. Okay, once again, the figure that I showed before, using all the data, and now for the zonal wind space-time spectrum. And this is for the westerly sample, and this is for the easterly sample. So here's everything again. So for the westerly sample, you can see that compared to using all the data, the Kelvin waves are actually propagating a little faster, and they're more discretized in terms of wave number, and the spectral signal is more narrow band than using all the data. When you look at QBO easterly sample, we have a broadband signal here, which is more like at about a 70-meter equivalent depth. One thing I should point out, by the way, is that you can see it probably a little better here, is that these Kelvin waves appear to be slightly dispersive. The power rolls off towards higher wave numbers here rather than following strictly this one equivalent depth. Okay, the difference in the phase speed between westerly and easterly QBO goes in westerly from 34 meters per second and easterly 70 meters per second. So we have a difference in the phase speed of about 8 meters per second, even though the difference in the strength of the zonal flow between QBO easterlies and QBO westerlies is more like 30 meters per second. So it's not just a Doppler shifting going on, but damping can also be used to explain this, at least qualitatively. So back to our expression for damping, and if we replace the frequency by the intrinsic frequency, which is based on the background flow, then we can come up with this expression where the Kelvin damping is shown to be proportional to the 1 over the frequency, essentially, based on the background flow as well. So the phase speed, this is just the gravity wave phase speed that you would get from the equivalent depth. So basically, what this expression says is that the damping increases at lower wave numbers and also as the phase speed approaches the background flow speed. So this expression blows up as the phase speed of the wave approaches the background flow, or in other words, a critical layer. And so, yeah, that pretty much, at least qualitatively, explains these changes when you plug in numbers from these expressions, as John Albers did here, where we have, again, a cubeo-easterly space-time spectrum. The damping is shown here in this little, hard to see, but this shaded region down here for the cubeo-easterly state. Oops. And here's the spectrum for the cubeo-westerly state, and the damping is now quite a bit larger in this region at low, especially low wave numbers and low frequencies. So essentially, the damping is working in this region of space-time and damping out these higher wave number and lower frequency modes, according to that expression that I showed earlier. Okay, now what we want to do here is look at the structure of these waves and how that changes with the background flow. And here we're doing a very straightforward EOF analysis. It's a covariance matrix EOF. For the Kelvin waves, we're filtering the zonal wind just to retain 2 to 25-day eastward signals only. And I'll show you that in a space-time picture in a moment. And so we get EOFs of just that equatorial zonal wind filtered in that frequency band. And then once we have the EOFs, we have principal components, which represent the time-varying structures that we come up with. And then we can take those principal components and project just through simple linear regression any other field that you like that would be dependent on those PCs. And we show statistical significance. I'll show you an example in a moment by plotting wind vectors. And again, we're going to condition these EOFs on the phase of the QBO using that same sample that I described earlier for plus minus 1 standard deviation of the zonal mean zonal wind. So here's our filter for Kelvin waves. So basically, we do a Fourier decomposition and zero out all the coefficients outside this box to obtain the Kelvin wave filtered zonal wind that we're basing the EOF analysis on. So yeah, when you do this, and yeah, one thing about this box is that it brackets pretty much all the different scales of the Kelvin signal that we saw earlier. So we can use the same filter for any height we like for this analysis. Okay, so we take the equatorial zonal wind, so it's just the zonal wind on the equator as the basis, and then we do the EOF analysis on that for that Kelvin filtered zonal wind, and then we project, in this case, at 50, okay, so we're doing this analysis here for the 50 hectopascal equatorial zonal wind, and now we're projecting the geopotential shown in shading and the zonal and meridional wind shown in vectors globally on that equatorial EOF. Okay, does that make sense? Okay, so interestingly, first of all, this not surprisingly, because we have that big spectral peak, this picks out Kelvin waves very nicely. If I show you the, again, the theoretical structure, we have a maximum in the zonal wind on the equator in phase with geopotential. The other interesting thing you might notice is that we have statistically significant signals in the extratropics as well. And that's a story for another day, but this is something we're very interested in and are also looking into. So once you have these EOFs, oh yeah, right. So in this case, when you filter for eastward only, you tend to get EOF pairs. And these pairs are highly correlated with each other at lag, and they're basically in quadrature. And for the case I'm showing here, EOF2 leads EOF1, so this represents an eastward propagating disturbance. So that's really handy because with the principal components for EOF1 and EOF2, you can square those, add them together, and take the square root, and that gives you a nice activity index for the Kelvin waves. And it's very useful and very interesting to look at with respect to other things like ENSO and so on, for instance. Another thing we're looking into here. Once we have, oh yeah, that's the other thing. This works really, really well for Kelvin waves. The EOF 3 and 4 is also a pair with EOF 3 leading, and this basically isolates the wave to Kelvin waves very nicely. Okay, and then you can do other fun stuff like look at the lag regression. This is for just PC1. Lag regression of the geopotential and the wind over time with respect to PC1 to look at how these waves evolve in this composite sense. Okay, so here, oh yeah, maybe I didn't mention it. This example that I'm showing here is for QBO westerly only. If we do the same thing for QBO easterly, this is what we get. So you can see, again, this isolates a Kelvin wave. In the case of QBO westerlies, we get almost a pure wave 1 signal coming out as the leading mode. For QBO easterlies, however, for one thing, the structure is much wider meridionally, and you can see that it tends to be more amplified over the eastern hemisphere, and it has higher wave number components, which was also implied in that spectrum I showed you earlier for the zonal wind on the equator for the QBO easterly. We had a broader, much broader band spectral peak for QBO easterlies than we did in QBO westerlies. So this is something that is systematic between QBO phases, and you can do some simple scaling by looking, for instance, at the equatorial radius of deformation based on the background flow. We have a phase speed, again, background flow here, and if we look at, for instance, just do some simple scaling where we take those zonal wind extremes, plus and minus 15 meters per second. For this example, just 100-meter equivalent depth in both cases. You can see that the radius of deformation is 6 degrees for QBO westerlies and 9 degrees for QBO easterlies. And that, if you double these numbers, this is just for the radius away in one hemisphere, double these numbers, that ballpark difference 12 versus 18 degrees width that we saw in these pictures here. So that, at least qualitatively, works out pretty well. Now, looking at the vertical, again, we're using the 50 hectopascal EOF based on the zonal wind at that level, in that Kelvin filtered band that I showed you earlier. And now we're just going to project, in this case, the zonal wind at all levels onto that principal component, in this case, the first principal component. And this is the structure along the equator for the zonal wind associated with that first EOF. So as you'd expect, you get upward and eastward tilted structures in the zonal wind. And this is 2 days prior to the peak in the principal component. And if I march ahead, again, as you'd expect, you get downward phase propagation, and over time, upward energy propagation. Not much signal initially up here in the upper stratosphere, and then over time, you start developing more signal, and these have larger vertical wavelengths up here, again, due to damping, and also due to the change in the static stability as well. So that seems to work out pretty nicely for this easterly composite. And then for the QBO westerly composite, the same thing. Most of the signal starts out down here in the lower stratosphere, even some signal in the troposphere that you can see in the upper troposphere down to 300 hectopascal. And over time, energy propagating vertically. But these vertical wavelengths are quite a bit smaller than what we saw in QBO easterlies. If I back up to the QBO easterly sample, that's what you get. And you can see these are less tilted, again, as expected from linear theory, and also narrower in the vertical. And again, some simple scaling. Here's an expression for Kelvin vertical wavelength. And if you, again, use 100 meters as an example, plus minus 15 meters per second, this probably overestimates the change in the vertical wavelength, but at least is qualitatively consistent with what you'd expect from linear theory. So Kelvin waves in easterly, according to this expression, should have a larger vertical wavelength, and that's what we see. Okay, so far I haven't mentioned anything about vertical shear, and I don't have time to get into that, but this is a meridional cross-section of the zonal mean zonal wind, for this case, QBO westerlies at 50, which peak here. You can see there's tremendous vertical shear, and that is also important for this problem. Going back to a paper by Jim Holton, for instance, and based on other studies which show that Kelvin waves are less affected by horizontal shear than vertical shear. In this case, what Holton showed was that after a wave passes through a westerly shear zone, so in other words, waves in westerlies would have propagated through a westerly shear zone, you should have vertical, less vertical, or a smaller vertical wavelength, and that the upward momentum transport becoming more concentrated towards the equator, which is what we saw in the structures of those waves in the two samples. Okay, same sort of thing for the antisymmetric zonal wind, which primarily isolates this mixed Rossby eastward inertial gravity wave signal. If we look at westerly basic state, we get a very strong spectral peak on both sides of the n equals 0 continuum here. These scale a little differently than on the Kelvin waves, and we think also damping has a lot to do with that as well. If we look at easterly basic state, so here's the difference from westerly to easterly, you can see the signal is much more concentrated around wave 0, implying that these waves are much less likely to these waves tend to have more of a standing characteristic, little more westward power here than eastward power here, but especially when compared to this westerly QBO basic state, where you have all this westward propagating power down here, which in the mean is the region where you have, because of the redness of the spectrum, much more power. You have westerly signals dominating. The expression for damping for mixed Rossby-gravity waves is quite a bit more complicated than it is for Kelvin waves. But essentially, this goes like the frequency cubed. So mixed Rossby-gravity waves are much more strongly damped in the vertical than Kelvin waves, which go by omega squared. And if you do the same type of calculation here for damping in QBO westerlies, here's the westerly peak we saw, and the damping lying pretty much out of the region where you have that spectral signal for the antisymmetric zonal wind. Here's the QBO easterly spectrum again, and then the damping in this case lines up very nicely with the region where you lose power here. So essentially, the damping just chops off the power over on this westward side, especially at low wave numbers. So that seems to work out, again, at least qualitatively. And finally, an EOF analysis for the mixed Rossby-gravity waves. In this case, we're using just a 2 to 6 day window for filtering, all wave numbers again. But for the, as I showed you earlier, for the mixed Rossby-gravity waves, since there are standing signals involved, you can't just filter for westward and account for the entire variability that you see in the data set. So again, the same procedure, except this time we're using 2 to 6 day filtered zonal wind here. The antisymmetric, that should say antisymmetric component. So that pretty much brackets the entire frequency range of the waves that we see involved in these mixed Rossby-gravity waves. And here's what we get for the leading mode in this case, which shows, as you'd expect, gyres centered on the equator and an antisymmetric zonal wind and geopotential height signal about the equator. So there's the theoretical, and that's what we see in ERA 5 for, in this case, QBO westerlies. So yeah, this is the QBO westerly sample only, and again, if we look at lag regressions, we can see that these signals do indeed propagate westward over time. And in the vertical, looking at the meridional wind along the equator for that first EOF, we see what you'd expect, these more or less zonally isolated signals. That's another thing I should point out. Another nice thing about doing this EOF approach is that it also shows you where these waves are most active, and this is the leading mode, which has accounts for by far the most variance, and these EOFs show up over the Atlantic sector and Africa, and that is where you see the maximum mixed Rossby-gravity wave activity in QBO westerlies. Here's the vertical structure of the meridional wind over time. So as you'd expect, upward and westward tilts associated with these westward propagating MRGs in QBO westerly, and downward phase propagation. Okay, so the same thing now for QBO easterlies. And this is the leading mode. So the first thing you notice is it's almost purely meridional flow. And you don't even have a geopotential height signal here until, okay, I'm going to go back one day from this leading mode here. This is 1 day prior. This is 18 hours prior, 12 hours prior, and so on. So what we're seeing here is a clockwise rotation of the meridional wind over time, with mass basically, sloshing back from southern hemisphere to the northern hemisphere, and then turning around and sloshing the other way over time. And this geopotential signal coming and going over time. And what's really going on, you can see in the vertical when you look at the meridional wind along the equator for that first EOF. You get this more or less standing oscillation maximized over the Western Hemisphere, mainly the Atlantic. And in this case, the meridional wind and the geopotential would show the same thing, is propagating purely downward. It's not propagating zonally at all in QBO easterlies. So if you're looking at 50 hectopascals like we just were in the previous plan views, what you see are these signals propagating down through that 50 hectopascal level over time. So to summarize, linear theory, at least qualitatively, works pretty well, and even quantitatively in some cases, to explain these changes in the structure and scales of these mixed Rossby and Kelvin waves with respect to the background flow. Damping, again, can be used at least qualitatively to explain increase in equatorial wave equivalent depth and phase speed with height, at least for QBO westerlies. In QBO easterlies, Kelvin waves have smaller equivalent depths and propagate more slowly and are wider meridionally and vertically, which of course has implications for forcing of the QBO itself. MRG waves are very profoundly affected by the QBO. They're significantly damped in easterlies with only low wave numbers surviving, as we saw in those plan views and in the vertical cross sections. And if we can trust them, reanalyses, I think, are very useful for looking at this type of basic state dependence. And as I mentioned earlier, also the temporal variability in these waves. But I think I also did mention earlier that for various reanalyses, you get very similar results for Kelvin waves, but that's not necessarily the case for mixed Rossby-gravity waves, and we're still kind of grappling with that issue. Even ERA interim looks quite a bit different than ERA 5 with respect to mixed Rossby-gravity waves. We get almost identical results for the Kelvin waves, however. But yeah, we're still trying to figure out why that's not the case for the mixed Rossby-gravity waves. Okay, I'll just stop there. Thanks.
Okay, we have time for questions.
Thanks, George. Really nice talk. I just want to ask a very dumb question. That is how to quantify the damping effect. Where does it come from? Because I'm not expert in this area. Could you explain that for me? Thank you.
Yeah, so I'm not an expert either in that. John knows more than I do, but maybe he could. It's primarily radiation, due to radiation, but there is also mechanical damping involved. And John, you have?
Formally, that expression is just cooling space, right? You just simply cooling, you have a temperature perturbation and it's radiating space. But that also works pretty well as a stand-in for when these waves go through a shear zone, right? Because the damping is going infinite as the phase speed approaches the background wind. And so, according to the damping expression, the damping is going infinite, but the other thing that's going on is that the waves are hitting a critical line.
Right.
So you should really think of that when those plots are up there. You should think of that kind of as a stand-in for those two processes.
So there's momentum absorption also taking place, and
In the shear zone.
yeah.
In the shear zone. Gotcha.
Mhm.
Thank you.
Other questions, comments? Mitch?
In one of your early papers here, you showed a considerable excitation from the troposphere. It kind of looked like a Madden-Julian oscillation or maybe a Kelvin wave. Could you comment on that? And the reason I ask this is because recently there has been some work done, for example, by Shidong Zhang, of a linkage between the Madden-Julian oscillation and the QBO. So do you have anything to say about this from your work?
Yeah, the MJO, that's a complicated question, and I don't really have an answer. The MJO, were you referring to a spectrum or?
Well, maybe your second slide or so. There was I can't remember what it was, early on, very early on.
Okay, yeah.
It says the second of that.
So, yeah, I mean, the QBO affects the MJO. The MJO probably affects the generation of these stratospheric waves. For sure it does. As Salvi and Garcia showed, even a red or a white spectrum of convective forcing will project onto these normal modes and excite them in the stratosphere. So whether the structure of the forcing matters or not, I think is a great question for these waves.
That would be a very good question to look at because of that work by Zhang, for example. It was kind of undefined really, but in ER5 perhaps we would get a more clear
Right.
answer.
Other questions, comments?
Rosie?
So all of this is dry, and I understand we're in the stratosphere, but I wonder if you've seen any differences on the Brewer-Dobson circulation, as well as on the stratospheric injections of water vapor when you have these differences in the Kelvin waves?
Yeah, we haven't looked at that. Hamid's papers, I would highly recommend you look through those because there is at least a strong signal of QBO there in the Brewer-Dobson circulation. But with respect to these waves, that would be a great thing, I think, to look at, what we haven't yet. Yeah.
Thanks.
Thanks.
So as kind of a newcomer to this area, why do the Kelvin waves have so much power, whether down low or up high?
Yeah.
I mean, it's likely
It's the well, you know, it's basically a gravity wave. It's equatorially trapped gravity wave. It's the simplest wave.
how does the atmosphere know that?
Right. Yeah,
Yeah.
yeah, yeah.
Yeah, I don't know. It's true in
There-
the models too that
Right.
they kind of Kelvin wave happy and
Yeah, I mean, if you look at almost any Hofmuller, like I showed, you'll see Kelvin waves. They're always there. But so are those mixed Rossby-gravity modes. I mean, the meridional wind just flops around all the time on the equator. And yeah, so I don't
well,
know.
anybody else who has that
That's a great
opinion or
question.
idea.
That's a great
Yeah.
question. Yeah.
Okay. Yeah.
There may be some answer to this in some respects, but to what Rich was saying, because this is about the MJO being effective. It's most effective in the maritime continent, Indian Ocean, and West Pacific. Whereas you showed a picture for Rossby waves is more in the Atlantic. So there's some sort of a classification of the wave types,
Yeah.
and it has a east-west sort of signal. Could you be definite about that and saying that in fact it's the Madden-Julian oscillation in the Indian Ocean, maritime continent, and Western Pacific that's driving all of this?
Yeah, I don't know. The Kelvin wave activity is, I have some preliminary results that seem to show that the MJO does drive Kelvin activity in the stratosphere, not necessarily in the troposphere. So yeah, I was thinking of showing that, but basically, if you, like I mentioned, you can get an activity index for the Kelvin wave, for instance. Times of high activity are associated with low OLR, enhanced convection over the maritime continent. When I first saw the picture, I thought, oh, this has got to be ENSO. But just 3 days ago, I looked at NEO 3.4 versus that index, and the correlation is 0. So, and I've only done this so far on a monthly timescale. So the plan is to start looking at it more intraseasonal.
That'd be good.
Yeah, yeah.
Okay. Volko.
So did I see that right? That most of the, or all of the group velocity is going upward? So is there any way for that signal to come back down into the troposphere and kind of mess with the weather? Or once it's in the stratosphere, it just goes up and doesn't affect us here in the troposphere anymore?
I mean, I think the similar arguments have been used to explain maybe the impact of the QBO on weather, where you actually get refraction. Yeah, I'm not sure. Not sure about. But that's a good idea.
Going back to this question of like how much can we trust reanalysis in the stratosphere, can you comment on just why there is more agreement with when it comes to the Kelvin waves versus the MRGs, and like observationally, like how well constrained this is, and why one would have the agreement and the other not?
Yeah, right. Maybe it does come back to the simplicity of the Kelvin waves that, you know, what we were talking about earlier with regard to Rosie's question earlier.
Okay, we're gonna have more time to talk out by the. Did you want to finish?
Yeah, yeah. If you know when Rolando and Murray did these numerical experiments, I believe that they found it very easy to excite Kelvin waves. So one possibility is that the first guess model finds it easier to mimic Kelvin waves and has more difficulty but with MRGs. But you know, a heck of a lot of satellite data goes into those analyses, so it's really, it's hard to understand why they differ so much from each other. You'd suspect that the first guess model is doing something there. But maybe the way the data are assimilated too has something to do with it. And from interim to ERA5 is quite a big change there as well. So, yeah, good question.
Yeah, I noticed that your first conclusion was the first thing, well, it was one of Jim Holton. The only time I saw Jim Holton lecture on this that was his conclusion. Linear theory works spectacularly well
Yeah,
up
right.
in the stratosphere. Anyway, thanks again, George. It was a wonderful seminar.